Uh, Good morning, students. Am I audible?
Yes.
Okay. Uh, and is this visible? Is the DIT algorithm on the board visible? Yes or no? Okay. If this is visible, now to explain the subtle differences or the unusualities in this signal flow graph, I have redrawn the yesterday's diagram here. Now, in the previous class, we discussed decimation in time fast Fourier transform. Now, how to obtain DFT or how to compute DFT from a discrete time input sequence by using decimation in time fast Fourier transform algorithm. And this is the fast Fourier transform algorithm for decimation in time to obtain DFT, discrete Fourier transform. Okay. Now, how did we develop each stage in this decimation? We had been through an equation set in the previous class. But in general, there were only two equations. I'll be shortly writing those equations. For each stage where we will be calculating the discrete Fourier transform, will be following only one set of equation, one pair of equation. Okay. First equation will be giving us the DFT points where these arrows will be pointing upwards. And the second equation will be giving us the DFT points where the arrows will be pointing downwards. First equation will be addition, second equation will be subtraction. We'll be going through that. Okay. But to begin with, yesterday there was doubt on if you observe this input sequence, x of n is not in the natural order. X of n is not in the natural order, but instead it is in the shuffled array form. Shuffled array form means x of 0 will be the first sample. We agree. But next sample has to be x of 1. But instead of x of 1, we are getting x of 4. Then we have got x of 2. Next, x of 6, and so on. Now, this is because that shuffled array form is because the input sequence was successively decimated. One 8-point sequence was decimated into two 4-point sequences, which contained only even numbered samples and odd numbered samples. Now later those two n-point sequences were further decimated into even numbered samples from those even samples and odd numbered samples from those odd samples. Okay. So because of that, we'll be getting this nature in the input sequence. Now I have written their equivalent representation in 2-point sequence as well as 4-point sequence. X of 0 is the first sample in the 8-point sequence, and it is first sample in the 4-point sequence, and it is first sample in the 2-point sequence. X of 4, which is the 4th or 5th sample in the 8-point sequence, when we convert or when we divide it into even numbered samples and odd numbered samples, then it will be F1 of 2, which will be V11 of 1. So the notation has been represented here. Now, the question was, will it be in the shuffled array form for all the algorithms? Now, for that, we need to understand its name, decimation in time. Now, to calculate DFT, input will be x of n and output will be x of t. From x of n, we will be converting it into x of t by applying discrete Fourier transform to calculate DFT by using decimation in time fast Fourier transform. Now, this decimation in time fast Fourier transform can be used to calculate IDFT as well, inverse discrete Fourier transform. Now, for inverse discrete Fourier transform, input will be x of k, or on the input side, discrete Fourier transform x of t will be the input, and output will be x of n. This from DFT will be obtaining its discrete time sequence back, so output will be x of n for IDFT. And this decimation in time fast Fourier transform can be used to calculate DFT as well as IDFT. And as the name itself indicates, here we are calculating the DFT in this signal flow graph. Decimation in time. Now, out of these two sequences, where is the input sequence? Where is the time domain sequence? Decimation in time. Time domain sequence has to be decimated. Decimated means decomposition, dividing it into even number samples and odd number samples. So, at the input side, we have discrete time sequence. So, it is in the shuffled array form. Now, it has a specific nature to it. We'll go through how do we obtain those bit reversed or shuffled array form. But for calculating DFT, x of n will be input. So on the input side will be the input sequence will be in the shuffled array form. Now if we use DIT-FFT algorithm to calculate IDFT, output side will be having time domain sequence. So output side will be in the bit reversed form. Input side will be in the natural order. Okay. Likewise, we have one more algorithm that we will be studying later, which is DIF-FFT algorithm. DIF stands for decimation in frequency. In decimation in frequency fast Fourier transform will be decimating the frequency domain sequence. So to calculate DFT, output side will be in the bit reverse form, and to calculate IDFT, input side will be in the bit reverse form. Now DIF-FFT will be exactly reverse of DIT-FFT algorithm, but we'll worry about it later. Did you all understand this? When the sequence will be in the bit reverse form or the shuffled array form. For it all depends on the name. Decimation in time. Time means time domain sequence has to be decimated. To calculate DFT, time domain sequence will be at the input side, so it will be in the shuffled array form. To calculate IDFT, time domain sequence will be in the output side, so output will be in the bit shuffled array form. If one of input or output, if they are in the bit reversed or shuffled array form, then the other one has to be in the natural order. Like here, input side is in the shuffled array form, so output DFT is in the natural order. Are you all following this? Are you all following this? Did you all understand? Now, if you observe the first stage from the input side, I have written it as V equals to 3. We'll come to what are these V values. V equals to 3, V equals to 2, V equals to 1. But if you observe the first stage here input is 2-point sequence and the output from this is 2-point DFT. So in the first stage, 2-point sequences or 2-point DFTs will be calculated for 2-point sequence. So the twiddle factor that we'll be using is W20. In the second stage, 2-point DFTs are the input. These 2-point DFTs will be combined to get 4-point DFTs. Okay, in the third stage, now here, because we are calculating 4-point DFT, the twiddle factor is used will be W40, W41 on both the sides. Okay, in the last stage, 4-point DFTs are combined to get 8-point DFT. So the twiddle factor is used are W80, W81, W82, W83. Okay, but when we want to calculate 8-point DFT, we'll be using only these twiddle factor values, depending based on the properties of the twiddle factor we studied. Twiddle factor is periodic as well as symmetric. Now we'll be using those properties here. Now what is the value of W40 or W80? W80 is 1. Likewise, W40 is also 1 and W20 is also 1. Okay, so instead of W20, we'll be using its equivalent value, that is W80. W20 will be equal to W80, the twiddle factor. Now by doing this, we'll not have to calculate the 2-point twiddle factor values, which will save us the computational time and computational, which will reduce the computational complexity as well. Okay, likewise, instead of 4-point twiddle factor W40, we'll be using W80 itself, because for both the values are same, which is 1. W40 equals to W80. And likewise, what is the value of W41? W41 is minus j. Now that same value will be getting for W8 as well, and it will be equals to W82, because W81 is 1 by root 2 minus j 1 by root 2, and W82, if you remember the complex plane that we had drawn in the first module, W82 will be equals to minus j. So instead of W41 in the second stage, we'll be using W82 in place of that, because again it reduces the computation of W41. Anyway, we'll be calculating these values. These values itself, their equivalent values itself, will be used to calculate the 4-point DFT and 2-point DFT. Are you all following this? Are you all following? Yes or no?
Yes, sir.
Any doubts, any questions? Any doubts, any questions? Now, what you need to understand here is, for decimation in time fast Fourier transform, to calculate DFT, input will be in the shuffled array form. Because input is in the shuffled array form, output will be in the natural order. Okay, and if you observe each of these three stages, you will find only one common structure, and that common structure is like this. Okay, in the first stage, all of these structures are individual. In the second stage, two have been overlapped now to get the appropriate output at the end. And in the last stage, 4 of these structures have been overlapped to get the appropriate DFT points. But the overall structure is similar to this one, where we'll be having the set of inputs. Let's say those inputs are A and B. And at the left side, we'll be multiplying it by some twiddle factor. Now let's call that twiddle factor as Wn to the power r. Now depending on the number of DFT points that are being calculated, this varies from 8, 4 and 2. Okay, and r takes the values 0, 1, 2 depending on the number of DFT points. Okay, but how the outputs are calculated? Now let's say small a and b are the inputs to this structure. Capital A and B are the output from that structure. Now, how did you calculate x of 0? X of 0 was f1 of 0 plus w80 multiplied by f2 of 0. Okay, in that sense, A will be, capital A will be small a plus w n to the power r multiplied by small b. Now, the nature of this equation is similar to what we had written for the outputs of each stage, for the calculation of DFT points of each stage in the previous class. And calculating the next part, that is f1 of 3 will be v11 of 1. I am just taking one example, and all the other structures are calculated in the similar manner by using the same expressions. So it will be v11 of 1. Because of this minus 1 being multiplied to the right side, it will be A. At this point, we'll be having the product B into W and R, but it will be multiplied by minus 1. So it will be A minus W and R into B. Now these two equations, these two are the general form of equations used to obtain the output of this structure. And this structure Because it seems like butterfly, it is called as butterfly structure or butterfly computation. Butterfly structure or butterfly computation to obtain the DFT points. Okay. Now for each butterfly structure or each butterfly computation, which will be used to compute the output of DIT FFT at every stage, will be having the set of inputs. Those inputs are transformed to outputs by these two equations. Upper point will be A plus WNR into B and lower point will be A minus WNR into B. For DIT FFT algorithm, these two equations are fixed. These two equations are fixed. So output at every stage will be calculated by these two equations itself. For every structure of butterfly, first output will be addition of the inputs, where the second input will be multiplied by this Quidel factor, and the second output will be subtraction, difference of the inputs, where the second input will again be multiplied by the Quidel factor. Are you all following? Are you all understanding? Yes or no?
Yes, sir.
Now this is called as butterfly operation. Using this structure to calculate the DFT is called as butterfly operation. Now the major point or the major advantage of using FFT algorithm is the real-time implementation of DFT is possible only because of FFT algorithm. Now I have discussed this point or stressed upon this point while discussing the advantages of FFT algorithms. Now how exactly it does that? Okay. Now to calculate or to perform one DFT operation, one butterfly computation, what all different arithmetic operations are involved? Okay. Now at this point, okay, what mathematical operation is involved? Here, B is being multiplied with this Quidel factor WNR. So here, one complex multiplication is involved. One complex multiplication is involved. And what is happening at this point? What is happening at this point? Here, A is being added to this product, that is B into W N R. So here one complex addition is required at this point. Okay. And what is happening at this point? What is happening at this point? So instead of multiplying -1 to this, what we'll do is we already have this product B W N R. So this is another complex addition itself. Now addition and subtraction are same. 2's complement addition will be subtraction. So subtraction will be treated as complex addition itself. Okay. So if you observe this, to compute one or to perform the operation on one butterfly will be requiring one complex multiplication and two complex additions. Two complex additions. So how many number of total complex multiplications and additions are required? Now observe the each stage. How many butterfly structures are there in B equals to 1? How many butterfly structures are here? How many butterfly structures are here? There are 4 individual butterfly structures which are overlapped. In the second stage, how many butterfly structures are here? There are 2 butterflies here and there are 2 butterfly structures here. And how many butterfly structures are present in the third stage? That is for B equals to 3. There are 4 butterfly structures which are individual. So for every stage in the DIT FFT algorithm, there will be n divided by 2 butterfly structures. Okay, and we have developed this for capital N equals to 8. So in the first stage we have n by 2, 8 by 2, 4. In the second stage we have n by 2, 4 butterfly structures. In the last stage also we have n by 2. 4 butterfly structures. So in each stage of decimation for DIT FFT algorithm, number of butterfly structures will be n equals to n by 2. For n equals to 8, this will be 4 butterfly structures. Okay, so how many number of butterfly operations that we need to perform? How many number of butterfly operations we need to perform in total for n equals to 8.8? The other day I said capital N will be chosen as 2 to the power V, or V can be written as log n to the base 2. If you rearrange this, we can write V as log n to the base 2. Okay. Now for n equals to 8, this can be written as 2 to the power 3, which will be equals to 8. That means V is equal to 3. V is equal to 3. Now for V equals to 3 means there will be 3 stages, 3 decimation stages in the butterfly structure or in the overall signal flow graph for DIT FFT algorithm. That is, this is 1, that is V equals to 1, this is V equals to 3, and this is, V equals to 2, and this is V equals to 3. So, the value of V represents the number of stages in the signal flow graph. And how many number of decimations that are to be performed? Those will be V minus 1. In this case, V is 3, so it equals to 2. So to obtain 8-point DFT, 2 times decimation has to be performed. First decimation is when 8-point sequence will be divided into 2 4-point sequences. And the second decimation is when those 2 4-point sequences will be divided into 4 2-point sequences. Are you all following? Are you all following?
Yes, sir.
Okay. So each stage in the DIT FFT algorithm will be having n by 2 butterfly structures, and there are V number of stages. V number of stages in the DIT FFT algorithm. So total number of butterfly operations. What will be the total number of butterfly operations that we need to use to compute n-point DFT? Those will be n divided by 2 into V, or n divided by 2 into V is equal to log n to the base 2. These many number of butterfly computations will have to perform, or these many number of butterfly structures will be in the n-point DFT computation of DIT FFT algorithm. Now that will be same for DIF FFT algorithm as well. Okay. So based on this, how many number of complex multiplications are required? How many number of complex multiplications are required? CM stands for complex multiplication. The number for each butterfly structure will be requiring one complex multiplication. So likewise, how many butterfly structures are there? Total number of butterfly operations are n divided by 2 log n to the base 2. So to compute n-point DFT, the number of complex multiplications will be n divided by 2 log n to the base 2. These many number of complex multiplications will be performed to compute n-point DFT. And how many number of complex additions are to be performed? Okay, for each butterfly computation will be requiring or will be performing two complex additions multiplied by number of butterfly structures. The total number of butterfly structures are these many, that is n divided by 2 multiplied by log n to the base 2. So 2 in the numerator and denominator will cancel. So complex additions, number of complex additions will be n multiplied by log n to the base 2. So to compute n-point DFT, to compute n point DFT, we'll have to perform n divided by 2 log n to the base 2 number of complex multiplications and n log n to the base 2 number of complex additions to compute n point DFT by using DIT FFT algorithm, which are far less compared to what we'll have to perform using direct computation method. Now we'll write the table to compare these two. But did you understand these two? ಅರ್ಥ ಆಗ್ತಿದೆ? Are you all following this? Yes or no? It is very simple.
Yes.
For each butterfly structure, one complex multiplication is required. So how many number of butterfly structures are there? Now that will be given by, for each stage will be having n by 2 butterfly structures. Likewise, there are 3 stages, which is represented by V. Okay. So n by 2 into log n to the base 2. These many number of butterfly operations will be present in one DIT FFT algorithm. So for each butterfly, one complex multiplication is required. So number of complex multiplications will be same, n divided by 2 log n to the base 2. And for each butterfly, will be performing 2 complex additions. So this will be multiplied by 2. 2 in the numerator and denominator will cancel. So complex additions will be n log n to the base 2. Now we'll compare this. We'll compare these values with the direct computation method. For direct computation method, how many complex additions and multiplications were required? To compute n point DFT, capital N point DFT, how many complex multiplications were required by using direct computation method? DC stands for direct computation. Complex multiplications required by n square and complex additions required where n square minus n. Now we had obtained these values, n square number of complex multiplications and n square minus n number of complex additions to compute n point DFT by using direct computation method. But by using FFT algorithms, how many complex multiplications are required? Complex multiplications are log n to the base 2 multiplied by n divided by 2. And complex additions are n log n to the base 2. N times log n to the base 2. Okay. Now, if we want to calculate 8-point DFT, by using direct computation method, 64 complex multiplications are to be performed and 56 complex additions are to be performed by using direct method. But if we use DFT, then we'll have to perform only 12, that is log n. Log n to the base 2 will be log 8 divided by log 2, which will be equals to 3. 3 multiplied by 4, that will be 12. And double of this, 24. To compute 8-point DFT, by using direct computation method, we'll have to perform 64 complex multiplications and 56 complex additions. But if we use FFT algorithm, we'll have to perform only 12 complex multiplications and 24 complex additions. So improvement rate is 5.3 times just for 8-point DFT. If we use 16-point DFT, if we want to calculate 16-point DFT, then by using direct computation method, 16 square, which will be equals to 256, and 256 complex multiplications and 240 complex additions are to be performed using direct computation method. But if we use FFT algorithms, we'll just have to perform 32 complex multiplications and 64 complex additions. So the improvement rate will be 8 times. Okay. Therefore, there was one more point in the advantages. As the number of DFT point increases, computational complexity of the or the time taken to compute the endpoint DFT reduces in the fast Fourier transform, and the computational complexity will also reduce in the fast Fourier transform. Now this is why. Are you all following this? Are you all following this? Okay. Now if you want to calculate 1024 point DFT, okay, by using direct method, we'll have to perform 10,48,576, that is 1 million complex multiplications and roughly 1 million complex additions. But by using FFT algorithms, we'll just have to perform 5,120 complex multiplications and 10,240 complex additions. Now compared to these two values, these are very less. So this is why by using FFT algorithm, we can implement the computation of DFT in terms of computer systems in real time. Else it was not possible. Are you all following? Are you all understanding the advantages of using FFT algorithm in terms of computational complexity and number of operations required, number of arithmetic operations required? And the next point that we need to discuss. Now all of these algorithms will be implemented on a computer system, and in these algorithms at every intermediate stage outputs will be computed. Now we need to store those outputs to be used as an input in the next stage. Okay, then because they are implemented in the computer system, what is the memory requirement and how computations are carried out? Okay, for each stage, now this is the generalized butterfly structure. W R A V, capital A will be A plus W N R into B, and capital B will be A minus W N R into B. Now compare these two equations with the previous one. That is, x of k was f1 of 0 or f1 of k plus W n k into f2 of k. First equation is similar to this. If you write it with respect to f1 of k, then it was equal to v11 of k plus w n by 2 to the power k v12 of k. And the second equation will be x of k plus n by 2, which was equal to f1 of k minus wn k f2 of k. This is same like capital B here. And if you want to write it with respect to f1, it will be f1 of k plus n by 4 equals to, say, v11 of k minus wn divided by 2 to the power k v12 of k. So there are only two sets of equations which will be of this form. So understand these equations better so that you won't face any problem while operating on these signal flow graphs for DIT FFT algorithm to compute DFT as well as IDFT. To compute IDFT, minor modifications are required. We'll go through that. Okay, once we start with inverse discrete Fourier transform. But to the point at hand, how many memory spaces are required? Okay, and how values are computed. Now, if you observe at each stage of butterfly, now in the first stage, to obtain 2-point DFTs, Those are V11 of k, V12 of k, V21 of k, V22 of k. Discrete time samples are used. X of 0, X of 4, X of 2, X of 6, X of 1, X of 5, X of 3, and X of 7. Once these 2-point DFTs are computed, these will be used as an input to the next stage to compute F1 of k and F2 of k. X of 0 through X of 7 are not required any longer. Are you all able to see this? Are you all understanding this? At every stage, the input will be required to calculate only that stage. Okay, that is X of 0 through X of 7 are required to compute V11 of k, V12 of k, those 2-point DFTs only. Then, in any further stages of the signal flow graph, X of 0 to X of 7 are not required. To calculate F1 of k and F2 of k, these are used 2-point DFTs, V11 of k, V12 of k, V21 of k, and V22 of k. And to calculate the last 8-point DFT, these are not required. V11 of k, V12 of k, and all 2-point DFTs are not required. Instead, these 4-point DFTs will be used, F1 of k and F2 of k. What it means is, to begin with, at the first stage, the inputs small a and b are required. Once capital A and B are calculated, will no longer need small a and b. So, in terms of memory location, we can store capital A and B. Okay, so we can store small a and b in some memory location. Once capital A and B are calculated, these will no longer be required. So capital A and B can be stored in the same memory location. They can be stored in the same memory location. A and B, because the lowercase a and b where it was stored earlier, because for further calculations they will not be required anymore. Okay. So this method, after calculating the new value, replacing it in the earlier memory location where the input was stored, is called as in-place computation. And fast Fourier transform uses it. Fast Fourier transform uses in-place computation. Okay. And how many memory locations are required? How many memory locations are required? Each value, if we assume A is a complex number, small a, and small b is a complex number, and likewise, DFTs will be complex anyway. So, for each value, we will be requiring two memory locations, one to store the real part and another to store the imaginary part. Okay. So, there are two inputs. For each butterfly stage, we will be requiring 2 into 2, 4 memory locations. For each stage, memory locations required for one butterfly will be 2 into 2, 4 memory locations, because 2 for A and 2 for B. Once these 4 locations, in the beginning, in these 4 locations, small a and b are stored. Once capital A and B are calculated, these same 4 memory locations or the values stored in 4 locations, that is small a and b, will be replaced by capital A and B. That is called as in-place computation. But 4 memory locations are required for each stage of butterfly structures. And how many butterfly structures are there? In each stage, in this signal flow graph, in DID-FFT algorithm, how many butterfly structures are there? Every stage has capital N by 2 number of butterfly structures. So for each stage, we will be requiring N by 2 into 4. So which will result into 2n. For each stage, 2n memory locations are required. Okay. So how many stages are there? Do we need to multiply it by b to calculate the total memory locations required? What will be the total memory requirement of the entire DIT FFT algorithm based on this? What do you say? Do we needing 2n memory locations for each stage? No, only 2n memory locations will be sufficient because FFT uses in-place computation. At the first stage, at the beginning, inputs will be stored in these 2n memory locations. Once the 2-point DFT are calculated, inputs will be replaced from these 2n memory locations to store 2-point DFTs. Next, once two 4-point DFTs are calculated, those two 4-point DFTs will replace the 2-point DFTs that are stored in 2n memory locations, and likewise. Okay, so, and we did not account for the twiddle factors that are being calculated. How many twiddle factors are there? There are 4 twiddle factor values, and for the other stages as well, we'll be using these 4 twiddle factors itself. For 2-point DFT, we'll be using W80, and for 4-point DFT, we'll be using W80 as well as W82. So, we'll be requiring only n divided by 2 butterfly twiddle factor values. N divided by 2 twiddle factor values. So, the maximum memory locations, the maximum memory requirement for an FFT algorithm, maximum memory requirement for an FFT algorithm will be 2n plus n by 2. Now this 2n is to store the intermediate results and n by 2 is to store the twiddle factor values. So the maximum memory requirement will be 2n plus n by 2. Any doubts, any questions? Any doubts, any questions? Any doubts, any questions? Okay, if not, the last part that we need to discuss regarding this signal flow graph is bit reversal. Okay, bit reversal is the important topic in fast Fourier transform algorithm because by bit reversal only we get the shuffled array form. Okay? Now, how did we get this? After x of 0, we should get x of 4 itself. After x of 4, we should get x of 2 itself. Now, how did we get this, or how did we end up with this order, with this shuffling? Okay, now that shuffled array form will be the result of this bit reversal. Okay, now what we'll do is, whenever input data comes into a computer system, now in the computer system everything has to be converted into binary form itself. Okay, now instead of saving the index in the natural order, it will be stored in the bit reversed order to obtain this shuffled array form. Okay, now what was the natural order of n? N is the index of discrete time sequence. Natural order of n was 0, 1, 2, 3, 4, 5, 6 and 7. For 8-point DFT, it will be from 0 to 7. Okay, index value x of 0, x of 1, x of 2, x of 3, x of 4 and likewise till x of 7. Now what will be the binary representation for this? If we use 3-point binary, n0 is the least significant bit and n2 is the most significant bit, then 0 in the binary will be 0, 0, 0. 1 will be represented by 0, 0, 1. 2 will be 0, 1, 0. 3 will be 0, 1, 1. 4 will be 1, 0, 0. 5 will be 1, 0, 1. 6 will be 1, 1, 0. And 7 will be 1, 1, 1. So this is the natural order of the input sequence and this is its binary representation. Okay? In bit reversal, what we'll do is we'll reverse this binary representation. In place of most significant bit, will be having the least significant bit and will reverse it. Okay, so bit reversal will give us, here we have N2, after bit reversal we will be having N0, N1 and N2. Most significant bit and least significant bit will be interchanged. Or we'll write this 3-bit binary representation in the reverse order. So reverse of 0, 0, 0 will be 0, 0, 0 itself. And reverse of 0, 0, 1 will be 1, 0, 0. Wherever you have N0, you substitute N2 and the other place. And reversal of 0, 1, 0 will be 0, 1, 0 itself. Reversal of 0, 1, 1 will be 1, 1, 0. Reversal of 1, 0, 0 will be 0, 0, 1. Likewise, this will be 1, 0, 1 itself, this will be 0, 1, 1, and last value will be 1, 1, 1 itself. Okay, now for this bit reversed binary representation, we'll convert this into its equivalent integer form. So 0, 0, 0 will be 0. 1, 0, 0 in decimal form will be 4. 0, 1, 0 in decimal form is 2. 1, 1, 0 is 6. And likewise, this is 1, this is 5, 3 and 7. Now how does these look? How does these look? How does they look? Now those are the index values of the input. First is x of 0. We have got 0 there. Next is x of 4, x of 4. Next is x of 2, x of 2. Next x of 6. And likewise x of 1, x of 5, x of 3 and x of 7. Now this shuffled array form is obtained by bit reversal. Now to obtain bit reversal, the natural order of the index of discrete time sequence will be represented in its binary form, and from this binary form will reverse the bits, or will perform bit reversal on this binary representation, and for those bit reversed will write the index values, which will give us the shuffled array form, and or this is also called as bit reversed form, which will be used for decimation in time fast Fourier transform as well as decimation in frequency fast Fourier transform. But what will you decimate depending on the algorithm differs. For DIT FFT, discrete time sequence will be bit reversed, and for DIF FFT, DFT, x of k will be bit reversed. Index of x of k will be bit reversed. How did we obtain this order for the input? Now this order is obtained because of bit reversal, and bit reversal is performed in that manner. Any doubts, any questions? Any doubts, any questions? Did you all understand? Artha aita?
Yes, sir.
Okay. Any doubts, any questions? No? Okay. We'll stop the class for today. We'll solve some problems on DIT FFT algorithm to calculate DFT, discrete Fourier transform, in the next class.